suppose f of x comma g of x are two continuous functions in their respective domains, and let something k is any real number, then point number 1, k into f of x is also continuous. Means if f of x is continuous and let k belongs to capital R, then k into f of x is also continuous function. Later, f of x plus g of x is also continuous, and f of x minus g of x is also continuous, are also continuous functions. Next, number 3, f of x into g of x is also continuous. Next, number 4, f of x divided by g of x is also continuous. To be understood that g of x should not be equal to 0. Okay. Next, one important theorem is there. If f of x is continuous, then modulus of f of x is also continuous, but converse is not true. That is, if modulus of f of x is continuous, then f of x is not continuous. For example, let us take f of x is equal to x. X means what? It is a identical function, identity function, or simply polynomial of degree 1. And one standard result is every polynomial function is continuous at x belongs to every real number. It is the most important point. According to this, okay, later we explain the standard continuous functions. First you listen. Every polynomial function is continuous at x belongs to capital R. Here we are taking identity function, means it is nothing but y is equal to x. X means what? X power 1. So it is polynomial of degree 1. So definitely it is a continuous function. It is continuous function. Okay. So what about f of modulus of f of x? Means it is mod x. Mod x, we can observe the graph mod x. Mod x says as it is plus x if x is greater than 0. That is equal to 0 if x is equal to 0. That is equal to minus 1 if x is minus x if x is less than 0. This is x, this will be y. So already I explained the modulus of x graph. So this is positive area, this is negative area, means minus x, modulus of x equal to minus x. So this is modulus of x, this is 0. So therefore everywhere it is continuous, no break in the graph. no break in the graph. Actually, this graph is not like that or is not like that. If it is like that, something break is there, something cut is there. So it is discontinuous graphically. But this graph is y is equal to x and y is equal to minus x. So this is modulus of x graph. So everywhere it is continuous. Therefore, modulus of x is continuous. Later, I will tell the same mod function about the continuity in standard results. Okay. Therefore, next converse. You come here. For example, f of x is defined as plus 1 if x greater than 0, and that is equal to minus 1 if x is less than 0. Here, what about modulus of f of x? Modulus of f of x means if x greater than 0 case, it is modulus of plus 1. If x is less than 0, it is modulus of minus 1. Modulus of plus 1 is 1. Modulus of minus 1 is also 1. So therefore, it is for all x belongs to capital R. Of course, we can define is equal to 0 also. So therefore, modulus of f of x equal to 1. 1 means what? Constant function. 1 means what? Constant function. So we did know the standard result. Every constant function is a continuous function. So therefore, modulus of f of x is continuous. Modulus of f of x is continuous. 1 minute. Here, left hand limit at x equal to 0 is LHL, that is equal to limit extends to 0 minus f of x. Left means 0 minus. 0 minus means that x less than 0. So that is equal to limit extends to 0 minus x less than 0 case is here. Then what is its value? Minus 1. So it is minus 1. So that is equal to minus 1 because it is pure constant. Next, right hand limit. Similarly, right hand limit at x equal to 0 is RHL, that is equal to limit extends to 0 plus x is greater than 0. This is f of x. So x is greater than 0 means it is plus 1. So limit extends to 0 plus 1, that is equal to 1. So therefore, LHL equal to minus 1 and RHL is equal to plus 1. So clearly, LHL not equal to right hand limit. Of course, f of 0 is equal to 0 case is minus 1. So therefore, left hand limit not equal to right hand limit. Therefore, f of x is not continuous at x equal to 0. So therefore, perhaps f of x is not continuous at x equal to 0, but modulus of f of x is continuous. So therefore, even if f of x modulus f of x is continuous, but f of x may not be continuous. It is the important theorem or point or statement. Some standard results are some standard continuous functions. We have to by heart these functions. These are always continuous functions. Namely, number 1, constant function. Number 1, constant function. It is always continuous function. Constant function means, for example, f of x is equal to something k for all x belongs to capital R. It's a graph. This is x-axis, y-axis. For example, this is the point k. So for every value of x, any real number means either x equal to 0 or x greater than 0 or x less than 0, it is always k. This is y equal to f of x equal to something constant k. K is a constant. K is a constant. This is constant function. It is always a continuous function for all x belongs to capital R. Next, number 2, polynomial function. Polynomial function. Polynomial function. This polynomial function is always a continuous function for all x belongs to capital R. So its form is f of x is equal to a naught into x power n plus a1 x power n minus 1 plus a2 x power n minus 2 plus and so on plus a n minus 1 into x plus a n. It is called polynomial function. Here x is belongs to capital R. So this is polynomial function. This kind of polynomial function is always continuous for all x belongs to capital R. Means what? That is, first f of x equal to something constant k. Every constant function is a polynomial of degree 0. Therefore, it is always continuous for all x belongs to capital R. Next, number 2. F of x is equal to identity function or identical function. It is nothing but that is y is equal to x. Of course, in geometry, it is angular bisector line passing through first quadrant and third quadrant, just like that. Its graph will be just like that. It is y is equal to x. So f of x equal to x, identity function. It is also a polynomial of degree 1. It is always continuous. It is always continuous for all x belongs to capital R. Capital R. Next, quadratic. For example, ax square plus bx plus c. The highest degree is 2. It is a quadratic expression or quadratic function. So this is also always continuous for all x belongs to capital R. Next, cubic means polynomial of degree 3. Ax cubed plus bx square plus c x plus d. It is also always continuous for all x belongs to capital R. So this is the section of polynomials. Next, all trigonometric functions, all trigonometric functions that is sin x, cos x, tan x, cot x, secant x, and so on, cosecant x, and all inverse trigonometric functions, that is sin inverse x, cos inverse x, and so on, cosecant inverse x, are always continuous in their respective domains. Means what? For example, tan x, example. Now is it visible? Example, tan x domain is what? Capital R, real number set, minus sin by cos means 2n plus 1 into pi by 2 comma n belongs to z. So this is the domain of tan x. Means what? Tan x is continuous function at x belongs to capital R minus set of means except odd multiples of pi by 2 and belongs to Z. So tan x is continuous function and x belongs to capital R minus the set of 2n plus 1 into pi by 2 comma n belongs to Z. So therefore similarly sin inverse x cos inverse x. Sin inverse x domain is what? Closed interval of minus 1 comma plus 1. So in closed interval of minus 1 comma 1 sin inverse x is always continuous. Similarly cos inverse x and cosecant inverse x domain x belongs to capital R minus open interval of minus 1 comma 1. In that area cosecant inverse x is always continuous. So therefore all trigonometric functions and all inverse trigonometric functions are continuous in their respective domains. Next, number 4. For example, logarithmic function. Log x is always a continuous function, but x belongs to capital R plus means at x equal to 0 it is not defined. Log x is not defined, and at x is negative values it is not defined. Therefore, x means log x is defined in R plus only. Therefore, log x is always a continuous function at x belongs to capital R plus. Next, number 5, logarithm of modulus of x. So, in this function, if we are taking x equal to minus 3, then modulus of minus 3 is equal to plus 3. So, log 3 is defined. Thus, it is defined means already I said in the functions x means what? X means if we are writing x means what? We are talking about the domain. Means the domain is belongs to any real number except 0. So therefore in this area log of modulus of x is always continuous. That is the complete meaning. Next, exponential function e power x. Only e power x, not e power 1 by x, just like that. Not e power 1 by x minus e power 1 by x divided by e power 1 by x plus e power 1 minus 1 by x. That is not only e power x. Exponential function. It is always a continuous function for all x belongs to any real number. Means at any real number e power x is always a continuous function. Next, number 7. Modulus of x is always continuous for all x belongs to capital R. Remember, not only modulus of x, x into modulus of x, comma, x minus k modulus. This kind of means modulus of x minus k. Modulus of x is always continuous function. X into modulus of x always continuous function. Modulus of x minus k is always a continuous function. Understand? Next, x plus or minus modulus of x is always a continuous function for all x belongs to capital R. So therefore, at x belongs to capital R, modulus of x, x into modulus of x minus k, x plus or minus modulus of x are always continuous functions for all x belongs to capital R. Next, about box of step function. Step function actually at the integer step x means limiting point extends to small a. Small a means a belongs to I. F of x or box of x, it is does not exist. Therefore, box of x at x belongs to capital I is not continuous. Therefore, except integer means box of x and another function is there, x minus box of x. Actually, it is denoted by simply fractional part of x. It is called fractional part of x. These two are always continuous at x belongs to any real number except integer. I means integer. So therefore box of x and x minus box of x, that is fractional part of x, it is always continuous at x belongs to capital R minus. Understand? Next, let f of x be continuous at x equal to c and g of x is continuous at f of c, then the composite that is g circle f of x means g of f of x is also continuous at x equal to c. So f should be continuous at x equal to c, and g of x should be continuous at f of c. Then g circle f of x is continuous at x equal to c. So therefore, for continuity of g of f of x at x equal to c, it is necessary that f of x is continuous at x equal to c and g of x is continuous at f of c. For example, g of x equal to something cos x, comma f of x equal to x square. Let us consider two functions. Here f of x is a polynomial function. It is a polynomial. Already I said every polynomial is continuous at x belongs to capital R at every real number. So therefore f of x is clearly continuous function. Next, g is what? A continuous function at x belongs to capital R, and g of x means every trigonometric function is continuous at its domain. Already said like that. So what is now the doubt is what is the domain of cos x? It is x belongs to capital R. So therefore cos x is also continuous at x belongs to capital R. Thus g of f of x means what? G of f of x means x square. So g of x square means g is what? Cos of, instead of x we are writing x square. So therefore cos of x square is also continuous at x belongs to capital R. So this is the continuity of a composite function g circle f of x at the given point x equal to c. 5.1. Examine the continuity of the function f of x equal to 2x square minus 1 at x equal to 3. Here f of x is equal to, it is given as 2x square minus 1, means it is a polynomial, of course, of degree 2. You need not write its degree. Is a polynomial. Therefore we know that every polynomial is continuous function at x belongs to capital R everywhere. Therefore here f of x is continuous at x belongs to capital R, that is at x equal to 3 also, since 3 belongs to capital R. So therefore it is continuous function at x equal to 3. Next question, f of x equal to 1 by x minus 5, x not equal to 5. Okay, actually f of x is equal to 1 divided by x minus 5. It is a rational. It is a rational function, and domain of f of x is equal to any real number except 5. So therefore rational function is also continuous at its domain. Therefore f of x is equal to 1 by x minus 5 is continuous at x belongs to any real number, means its domain. Hence the problem. F of x equal to x square minus 25 divided by x plus 5, comma x not equal to minus 5. For example, if x equal to minus 5, then minus 5 plus 5 0, denominator is 0, then f of x is not defined. Okay, we can do this problem by using two methods, namely first method 1. Here f of x equal to x square minus 25 divided by x plus 5. Actually it is something g of x divided by h of x, means numerator is polynomial, denominator is also polynomial. Therefore this f of x is a rational function. So therefore rational function is also continuous in its domain. Here domain is any real number except minus 5. So therefore f of x is continuous at x belongs to capital R minus the set of minus 5. Okay, this is the first method. Second method. F of x is equal to x square minus 25 divided by x plus 5, comma x not equals to minus 5. X not equal to minus 5 means that x plus 5 is not equals to 0. So therefore it can be expressed as x plus 5 into x minus 5 divided by x plus 5. So since this value not equal to 0, we are permitted to cancel like that. So it remains only x minus 5. So therefore f of x is equal to x minus 5. Of course it is a polynomial. It is a polynomial of degree 1. So therefore clearly every polynomial is also a continuous function for all x belongs to already we said about x belongs to capital R minus the set of minus 5. Hence the problem.